This video is about finding volume using cylindrical shells. As always, begin by reading carefully through the textbook and taking some good notes, but now consider the following highlights for this topic. Let's recall that recently we've done topics using disk and washer methods for finding volumes of solids. Well, the problem is that those don't always work well. For example, let's consider the following. If we wanted to find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals 3x squared minus x cubed, and the x-axis, what would happen? Well, if we take a look at the simple graph of this region, we have this curve graphed that is y equals 3x squared minus x cubed, and we're just showing the kind of quadrant 1 space of this because we're also bounding it by the x-axis. If you were to rotate this region about the y-axis, of course we have x-axis horizontally, y-axis vertically. If you're going to rotate this region about the y-axis, because of the space that we see between the graph and the y-axis, when you rotate it, which let me draw the symmetrical version of it roughly, it would look something like the same thing on the opposite side, but it'd be all spun around. And when you do that, it would need then washers if we were looking back or thinking back to what we were doing previously. So let me draw in a washer cross section on this region. And again, because of the space that we're seeing in the middle between the y-axis and where this curve is, when you rotate it about the y-axis, it would create a hollow middle. And that's the point about the washers. So if you were to rotate it, we would end up with a washer. Now that's fine because we know how to handle washers. Problem with this washer though is as follows. Let me redraw this like we've been doing. I'm going to just draw a cross section of this washer, which is really just a hollowed out cylinder. I'm going to give it some thickness. As we know, we have to deal with the thickness as well. Give it some ridges on that thickness just so we can kind of see the 3D-ness of it a little better. So here's the problem with this kind of washer. So the thickness, notice, is a vertical thickness for this washer, which would be a dy, and that's fine. The radii, however, are where it gets a little challenging. So if I extend from the center of the washer to the inner radius, we've been calling that like this, the lowercase r radius. Or if I extend from the center to the outer radius, we've been calling that the capital R, the larger radius. And in order to create an integral of those, since those are x distances, they're horizontal in nature, based on the way that this washer is being stacked. You know, these washers would be stacked vertically on the y-axis, the axis of rotation, which means that those radii would be all horizontal measures, or in other words, x values. Problem with that is, in order to take the original given equation for this curve, if I have y equals 3x squared minus x cubed, which is again the originally given function for this curve, can we solve that for x so I have x equals something? Well, not easily at all. So that's the problem. Our algebra is going to limit us here. Now, is it impossible? No, you can find a way to do this, but it's nowhere near familiar to us using the algebra that we have readily available. So we're going to say that since that is so challenging or nearly impossible, this method for finding the volume of this solid is actually not preferable. So it necessarily would create these washers. We know how to find volumes of washers. Problem is, the process of doing it, which would involve setting up the integral, is going to involve solving our function for x, and that's not something we can do. So what we're going to do is now look at another method that will allow us to handle things like this. So now our method is called the shell method for finding volumes of solids. Let's recall some geometry we're going to need here. So geometry for a cylinder is as follows. The volume is pi r squared h. Now that's just area of the base times the height. That's nothing too earth-shattering for us. We've been using that kind of thing already. But now we're also going to incorporate something else, which is the circumference of a circle, which is 2 pi r, r being the radius, and h, of course, being the height of the cylinder for the volume formula. We're going to have to combine all of these geometric formulas. They're basic, formulas from high school geometry or even earlier, but they're going to come in handy for us here. So again, I'll say them. Volume equals pi r squared h, for that is volume of a cylinder. Circumference of a circle, which happens to be the base of the cylinder, is 2 pi r. The radius, of course, that's what r is, and then h is height. Now, the definition of a shell is a hollowed out cylinder, which is why a lot of these formulas are going to make sense. Its volume, that is the volume of a shell, if it is indeed a hollowed out cylinder, will be the following. It's the outer shell volume with the larger radius, take away or minus the inner shell volume with the smaller radius. Now, it's helpful to look, I think, at a picture of a hollowed out cylinder. So let's do just that. Imagine drilling out the center of a cylinder so that you have a cylinder on the outside and really a cylinder on the inside that's just hollowed out. As we've been doing, you can give these radii some labels. Let's do that. So if I go from the center of the hollowed out cylinder all the way to the outside of it, that would be the larger radius. We'll call that capital R. If I were to go to from the center to the inner radius, we'll call that lowercase r, the smaller radius of the two here. And if we put those in place, let's do a little bit of algebra. This looks worse than it is, I promise. But all we have here are two things, as described already. We have this outer shell volume, which has the capital R radius. That's just pi r squared h, again going back to the volume of a cylinder formula we recalled above. But then take away the inner shell volume, which is again pi r squared h, but this is a lowercase r for the, in this case, smaller or inner radius. Now, if we do a little bit of algebra with this, it can turn into a convenient sort of formula for us. That's what we want to do. So notice what would happen here. If I just take what we just described, the volume of the outer cylinder minus the volume of the inner cylinder, and I factor out what's common to both of those terms, that would be, of course, a pi, which I'll factor out to the left or in front of our expression. And then notice they also have in common an h. For height, I'm going to factor that out but write it at the end. So our result is this, pi, and then in brackets, capital R squared minus lowercase r squared, close brackets, and then h. Just doing a little bit of basic algebra to rewrite the general idea of subtracting the smaller inner volume of the cylinder from the outer one to get this hollowed out, what we're calling a shell. Now, if we do a little bit more algebra on this, this is where it can get even more convenient. Again, it's not maybe obvious to try this, but it helps out once we get to the end, as you'll see. So now let's take a look at what's in the brackets from what we just factored previously. This capital R squared minus lowercase r squared. That's just a difference of two squares in algebra, which we could factor to be capital R plus lowercase r times capital R minus lowercase r. Again, that's just difference of two squares getting factored. But then, if we even look at this a little bit further and do some, this is where it gets like, well, you might not have thought of this had I not mentioned it, and same with me, actually, right? But here's a convenience step we could take. I'm going to multiply this entire expression by 2, but then also divide it by 2, which means those are kind of offsetting each other, so I'm not actually changing the expression numerically. I'm canceling out what I've done here, but why would we even try this? Well, because what it does is create in one of these factors here, capital R plus lowercase r over 2. And you may say, well, what's the point of that? Well, that's just a convenient way of writing what we call the average radius. Average radius, which happens to be a convenient way of labeling our picture. So if I now take the average radius, that's just going from the center, let's say, to the middle of where the thickness of this shell is. So I'm going from the center, not to the outer nor the inner, but to the middle of our shell thickness. It's kind of hard to draw with a thickness that's small, but that's kind of where it's heading. So this average radius is going from the center to somewhere in the thickness of the shell. We'll call it right in the middle, the average of that. Okay, so that expression is going to be helpful for us because we can use a single variable to represent that average radius, as we will see shortly. Now let's continue with this algebraically. If we then, let me see if I can use this same color here to say our average radius is now one of our factors. And I'm going to just give it that verbal name here for a second. And then notice if we keep all the other factors in place, we had an h factor, that's just the height. And then we have this also this shell thickness, which is really just capital R minus lowercase r. That's the thickness of that shell. That would, of course, wrap all the way around the shell. Now, again, why are we kind of messing around with all of these expressions or definitions? You'll see eventually that this is a very convenient way to use the volume of this shell. If we put it all back together, what you're seeing then is we have 2 times pi times average radius. Well, if you go back up, remember we said 2 pi r was our circumference formula for a circle. So really that's just the circumference of the shell times the height, just the height from one base to the next of the shell, and then times the shell thickness. Okay, so again, why is this more convenient? Well, you'll see very shortly that I think it really helps to write it this way, eventually in symbolic form, as you will see. Let me label in our diagram here the height. I'm going to put this in like a pink color just to get these coordinated, color coordinated clearly here. So we have the height of the shell, which is also just the cylinder, and that height we'll call h. We have the shell thickness. I've put that in orange. And then we have this circumference, which is there because of the way the formula is. I'm not going to draw it into, I'll use that same blue color. That's just wrapping all the way around the cylinder, but we're using the average radius for that, so it's actually kind of going right through the middle. It's too hard to draw, but it's a circumference going right through the middle of the thickness of the shell. Okay, so those geometric components or metrics or labels are what we're using for all of this. As you will see soon, this does turn out to be a very convenient way to label this. So we'll boil this down to a symbolic formula here in a second. But for now, I'm just trying to show you where this comes from. So it's not like, wait, where'd that formula come from? Right? This is kind of where it's all coming from. Just some algebra on the basics here. Now, shells can expand from a vertical axis of rotation, such as the y-axis, of course, or horizontal. We'll see both here. But if you think of these shells expanding from the vertical axis, then let's look at a diagram of course, a horizontal x-axis, a vertical y-axis, and what we're going to imagine is that on the y-axis we're stacking up these shells to form what would look somewhat like a layer cake. Think of like a large wedding cake of some sort, or some kind of layered concentric cylindrical cake. So you have these shells that are all kind of stacked within each other. If you pulled out a couple of them, it would look like one is, right within the other, but maybe extending a little bit beyond it, higher, creating these kind of layers. But of course, one of those shells is what we've already analyzed, being this hollowed out cylinder. Now, remember all that work we did earlier, and I said it was going to get easier? Well, here's what I'm talking about. The formula we're going to use for the volume of this entire layer cake is going to be as follows. Volume is going to be the definite integral from a to b, okay, we'll see where those come from shortly here, of the circumference, that's 2 pi r, times the height times the thickness. Remember we said that above? That was exactly our formula, circumference times height times thickness. Well, that's exactly how we can put this all together, 2 pi xy, and then if indeed you have these cylindrical shells that are expanding vertically, of course in that case your thickness would be a dx, a horizontal thickness, because it's extending in a horizontal direction, and that's why this version of the formula has a dx to it for the thickness of the shell. Now again, that's going to determine our variable of integration. It all starts to tie together, but we're seeing now that when you expand from a vertical axis, you have a horizontal thickness, a dx. Let me label that as thickness so we keep that straight. Thickness, which is something we've been using even in our previous topic with the discs or washers. We talked about thickness. And so in this case, it's a horizontal thickness, dx. Well, or you can expand from a horizontal axis for these shells. And if doing that from a horizontal axis of rotation, such as the x-axis, the picture just kind of turns over onto its side. So now we have a horizontal x-axis, and we're extending out from that x-axis to get the radii of these cylindrical shells. Of course, you have a vertical axis that's still kind of lurking there. If these shells are stacked now, you could say almost like on their side. In this case, then, the radii would be all extending vertically, and the thickness this time would be a vertical thickness, dy. And so you'll notice this time a dy showing up in our integral. So this is a very similar setup for the volume of this cylindrical shell, this layer cake of them, of course, on its side. Now it changes the orientation and which variables go where. But here's what's beautiful about this setup. Okay, so finally, here's how the value, I think, finally comes in from doing all the way back to doing all the algebra we did to, factor out the pi's and the heights and all that stuff. That's all showing up now as value in the following formulas. Notice they're about the same, except one slight difference. They're both the definite integral from a to b of 2 pi xy and then d whatever. So in this case, it's a dx if your thickness is horizontal, or it's a dy if your thickness is vertical. But notice what's in front of those is the same in either case. 2 pi xy, 2 pi xy. So that's going to be a familiar setup for us that is easy to remember and even easy to use with, of course, a little bit of algebra involved to make sure we have the correct variable given the function we have in the problem and all that. But we'll see that shortly in some examples. But the 2 pi xy just kind of sounds nice, kind of rhymes. The pi and the y rhyme. So that's kind of how the, I think, value of this little setup will show up. 2 pi xy. Now, let's see some examples of how this actually works so that we can use the calculus we already know in order to find these volumes for the solids provided. Our first example says the following. Use the method of cylindrical shells. Okay, so this time they're actually just straight up telling us what to use here. Use cylindrical shells, that's what we had above, to find the volume generated by rotating the region bound by the given curves about the y-axis. All right, so we're given an axis of rotation, and then we're given the following curves. So we have y equals the square root of 5 plus x squared. That's all within the square root there. Then we have y equals 0, x equals 0 and x equals 2. So let's start, as always, with a basic picture to work with here, just to make sure we can understand exactly what we have going. Based on what they gave us, I'm going to draw, of course, a horizontal x-axis, vertical y-axis, and then let's draw some of these constraints as provided. So the first was y equals the square root of 5 plus x squared. Now that may not be a super familiar looking kind of graph, but without much trouble, and even maybe using a graphing utility to confirm the visual on this, you could plot some basic points to get this. So for example, we're looking for nice square numbers to go underneath the square root. So notice if I had the square root of 9, that would be convenient. So you could make a basic table to say, like, well, if x were 2, then I plug that in. 2 squared is 4, 5 plus 4 is 9, square root of 9 is 3. So that means I do have a point at 2 comma 3. We can just plot that there. Now you may say, well, what about when x is 0? Well, it's not going to be a pretty number. You'll have square root of 5, which is something you could actually compute and estimate. The point is, it's certainly less than 3, bigger than 2. So, you know, let's just estimate somewhere in there we have square root of 5 for our y-intercept, 0, square root of 5. And if you were to extend this graph to the point 2 comma 3 that we know is on there, we would end up with a curvy looking kind of graph. Again, you can kind of verify that in a graphing utility just to get the visual of it. That's one of the boundaries of this region, right? Y equals the square root of 5 plus x squared. Now another boundary is y equals 0. Well, that's the x-axis, so that's easy to work with. X equals 0, that's the y-axis, so that's easy to work with. And then x equals 2, which happens to be a vertical line right where we already were, right? Remember we used 2 as an input to plot a point? Well, if I extend a vertical line down from where our point of 2 comma 3 is, that vertical line is going to be like a wall bounding this region. So we end up with this interesting looking, you know, curved on the top, kind of squared off on the sides and bottom shape. And this region is going to be rotated about the in this case, rotating the region bound by the given curves about the y-axis. So I'm going to take this region and rotate it about the y-axis. Well, when we do that, notice what would happen then, right? If you kind of imagine this happening with all these features, if I go to the point 2 comma 3, if I were to rotate that around, then symmetrically it'd end up at negative 2 comma 3 as well. So you can imagine this whole region being rotated around, and then all the way around would create this three-dimensional solid, and that's what we're trying to find the volume of. So even the bottom would rotate all the way around. Now in doing that, we were told to use cylindrical shells, so we'll do that. We need to basically understand the components of this. Notice then, if I were to create some shells on here, which I think I'm going to try to draw for this first example. It's not always easy to draw these, especially because the visual can get challenging and almost worse, right? But if you imagine the outermost shell, imagine it having a thickness to it that would be almost right where the full region is. I'm going to draw in a thickness to this outermost cylindrical shell. Now, inside that cylindrical shell would be a smaller radius one. Remember, we're working at the layer cake here thing. So you can imagine then a smaller radius cylindrical shell. These would just become concentric cylindrical shells that kind of spiral down inside. Not really spiral. They just kind of work their way down inside this figure, filling it up eventually. So if we were to pull out one of these such cylindrical shells, remember it just looks like a cylinder as we had drawn above. So let's see, I'm drawing a cylinder as kind of like drawing an oval, and then draw the two sides to it and the bottom that matches the curvature. And then you have a thickness to it, so I'm going to draw that in. And that thickness, of course, in this case, because the way that these are extended, would have a horizontal thickness, a dx thickness. We would have a large an average radius that would go from the center of the shells all the way to the middle of the thickness. Of course, that would be a horizontal distance. So we'll call that the average radius, as we've just been discussing above in our formula. So the point is it's an x value because it's horizontal. That's what's key to remember here. And then, of course, we would have a height. Put this in here. I'll just use that same pink. Try for that same pink color for the height that we used above. And that height, of course, would be a y value. I'm just trying to connect this with what we drew or listed above to get all the geometry in the right spaces. So we have an x value for our radius. We have a y value for our height. We have a dx for our thickness. All we have to do now is go back up to our little formula and put things in place. Remember, we said above that volume is going to be the definite integral. Now, if this is a dx thickness, then that's going to be our variable of integration. So we'll put that in place. That helps us remember exactly what we're working with for the bounds of integration. We're going, in this case, all the way from 0 to 2 on the x-axis. I'm going to put these in here, 0 to 2. That's going from where we have these x values on our x-axis. And I want in that, remember, it's just 2 pi xy times, in this case, dx. Where do we get the dx? Because that's the thickness. How do we know it's dx? Because of the orientation of these shells. So this is all hopefully tying together. If you go back to these formulas we wrote above, remember, it's always just 2 pi xy as the integrand, and then times the thickness, which is either a dx or a dy. Well, if you have vertically oriented layer cake, like we do here, where your radii are extending from the y-axis, which is the axis of rotation, then your thickness is going to be a dx, which is, again, the first case we kind of started with above in our formula there. So that's what we're using, 2 pi xy dx in this case. And then the only thing we have to do next is make sure that all the variables in our integrand match the variable of integration, just doing a little substitution. So obviously with the variable of integration being an x, I don't want a y in my integrand, so all we got to do is replace y with, well, in this case, it's given quite clearly to us as the equation of that curve, y equals, we want it in terms of x, and that's what's given to us. It's the square root of 5 plus x squared. So we'll simply rewrite this as the integral from 0 to 2 of 2 pi x, and then instead of y, we're going to put it as the square root of 5 plus x squared. Again, that's given in the problem above. Let me highlight that just so it's clear. We were given that y equals the square root of 5 plus x squared. So instead of y, we write exactly that. Just basic algebraic substitution here. Now the goal, of course, is to compute this integral. But it's getting better. So now this is, of course, a dx. Make sure that's in place. We should be able to handle this integral with a basic u sub. So let's do that work over here. We'll let u equal the inside of the square root. So in this case, 5 plus x squared. That means, of course, du equals, if I take the derivative of 5 plus x squared, I just get 2x dx. Remember, it's really du over dx. If you multiply both sides by dx, we get du equals 2x dx. This is just a classic u sub type problem. Now, why was this convenient? Well, because if we finish off this integral, we're going from 0 to 2. And notice the convenience here. We have 2x dx getting replaced with du. And in fact, there's a 2x dx in our problem. Now, the pi being a constant, of course, can just float to the front. Get that out of the way. And that leaves nothing but the square root of u, or in other words, u to the 1/2. Let me put it this way, square root of u du. So we're just using a basic u sub here. If I want to finish this off, of course, it's more convenient to say this is really pi times integral from 0 to 2 of u to the 1/2 du. Oh, hold on, I didn't fix our bound. Let me go back and change these. Remember, we used a u sub, so we have to change our bounds. Hold on. So if u was really 5 plus x squared, then we had 0 as our lower bound. So our new bound is going to be u equals 5 plus 0 squared, which is, of course, 5. So our new lower bound is 5. Our new upper bound, similarly, would be, well, 5, plus, it was 2. Previous bound was 2 for the upper bound. So now it's going to be 5 plus 2 squared, of course, that's 5 plus 4, or 9. So our new integral after the u sub is going from 5 to 9. Let's fix that. And so now we can handle this integral using the fundamental theorem of calculus. Not too bad here. So this is really just pi times the antiderivative would be, well, for u to the 1/2, we'll add 1 and divide by that power. So 1/2 plus 1 would be 3/2, which means now we have 2/3 u to the 3/2. And this is going from 5 to 9. Okay, so fundamental theorem here, right? Add 1 and divide by the new power. Add 1 to the power and divide by it. So 1/2 plus 2/2 is 3/2. Divide by 3/2 is the same thing as multiplying by 2/3. That's where that's coming from. The pi constant just stays out front. Nothing happening there. And then we have these this antiderivative we want evaluated from 5 to 9, which are, of course, the new bounds. So let's put this together. We have pi as our constant out front. And then we have, let's see, plugging in 9 for u first, and then take away 5. Okay, let's just put this kind of, I'm going to put the final step down. So this will really just be 2/3 times pi. All those constants just float to the front. And then we would end up with 27 minus 5 to the 3/2. Again, that's just plugging in 9 for u, and then subtract plugging in 5 for u, factoring out the 2/3 and the pi, and this is our exact form answer. You can approximate that. You can double check it with a calculator to match those, but that should do it for the volume of this solid using the shell method. Our second example is the following. Use the method of cylindrical shells. Okay, we're being told that again. To find the volume generated by rotating the region bound by the given curves about the x-axis. The curves provided are y equals x to the 3/2 power, y equals 8, and x equals 0. Well, like we've been doing, let's start by getting a basic graph drawing of this region so that we know what we're working with. We'll draw out a horizontal x-axis, a vertical y-axis, and then take a look at these provided curves. Now, some of them are pretty simple, right? Y equals 8. That's just a horizontal line going through 8 on the y-axis. You can kind of just imagine that in there. X equals 0. That's just the y-axis. And then this other curve, y equals x to the 3/2. That may not be a familiar looking graph. It's not a polynomial, but it's not terrible to graph. So let's make some basic points on this one. So like, for example, if I were to draw an x, y table, when x is 0, so is y, plug in 0. So 0, 0 is a point on this curve. And then we'd want to know, like, well, where does it maybe intersect this horizontal line y equals 8? So if we simply set those equal, so let's say if I have y equals x to the 3/2, which is what's provided, but I let y equal 8, which is where that horizontal line is, then I really have 8 equals x to the 3/2. If I do some basic algebra on this, such as raising both sides to the reciprocal power of 2/3, reciprocal of the given 3/2 power, that is. But when you multiply those powers, of course, they cancel, giving you, in this case here, 8 to the 2/3. Well, the thirds the denominator is the root, so cube root of 8 is 2. 2 squared is 4. So this means 4 equals x. So that means when x equals 4, y equals 8, which gives us another point to work with. And then what the curve looks like between those, we're not going to get too much more precise based on other points, but we know it's going to be slightly curved. You could use a graphing utility to kind of verify that. It just looks, it's not quite like a polynomial or a parabola, but it is curved in some way like that. So that's what we have. Notice then we're bounding that region, so the curve y equals 8, that's kind of like the roof of it, the top of it. X equals 0, that's the y-axis. So we're looking at this kind of solid object here in the quadrant 1 zone. But we're rotating this about the x-axis this time. So again, symmetrically, if you were to kind of rotate that down, we have a point at 4, 8. That means we'd have another point at 4, negative 8. Let me extend my vertical axis so I can have some space to work down there. And let's put this in. So we have the point 4, 8, which means 4, negative 8. Symmetrically, then let me just kind of put that down there so it looks believable. 4, negative 8, there'd be a point, and this object would be, symmetrically drawn and rotated down that way. So it ends up having what you could say is maybe like a hollow middle, but the middle now is extending out in a horizontal direction. So since this is changing the way that it's rotated, we have to make sure we understand how these shells will show up. Let's do that by trying to draw one of them, right? So if I imagine a shell, now I'm going to draw one just kind of in the middle. I think it's just easier to see that way. So somewhere in the middle of quadrant 1 where we drew this original zone that's being rotated about the x-axis, I'm going to draw a shell that would extend out. So the height of this shell, it's now kind of on its side. So the height is actually an x distance. And then you could say that if I draw in a cylindrical shell, of course, its shell has a hollowness to it, and therefore a thickness to the rim of the shell. So I'm going to draw that in there as best I can. We want to understand what's going on. Well, notice the thickness of this shell is going to be a vertical distance, which would be a dy for thickness. Again, those things matter because we have to be able to set up our integral, and that, of course, is a key component, the thickness, the variable of integration. Now, we also have a radius. Of course, we're using an average radius, but we're kind of disguising that with our little formula. The radius would go from the center of this shell to the middle of the thickness. And notice then that radius would be a vertical distance. So that radius would actually be a y, or vertical distance. So all these things matter because we have to put in or set up the integral. So let's do that. All right, so let's set up our volume integral here. We know volume equals the definite integral from, well, let's hold on for a second to make sure this is all lining up. As we already discussed, based on the thickness of our shells being a dy, that's going to determine the bounds of integration, because that means y is the variable of integration. Well, our radii go from nothing in the middle all the way out to 8 at biggest. So we're going to go from 0 to 8 for these radii, extending out from the x-axis to create these cylindrical shells, these kind of layered wedding cake type shells. Of course, this one looks like it's imploding in the middle because of the way it's hollow in the middle there. But we have our integration from 0 to 8 of the standard formula we have above, which is 2 pi xy. And in this case, it's a dy as discussed already. So if that means, if our integration variable is y, if we're doing dy, that means that every variable in our integrand should also be a y, which means the x that we have in our 2xy, or 2 pi xy, that needs to be converted over to a y in some way. So we need to do a little bit of algebra here, but it's not terrible because we already have the following. We know that y equals x to the 3 halves. y equals x to the 3 halves. That was just, again, given as the definition of that curved boundary. And all we have to do is solve that for x equal to something in terms of y, which means we already did some of the algebra above, but we just did it numerically. So let's redo that. If I raise both sides to the reciprocal power, I have x to the 3 halves. If I raise that to the 2/3, of course I have to do this on both sides, then the 2/3 and 3 halves cancel, which means we have x all by itself, and this is looking good. So that means we have x by itself equals y to the 2/3, which means I can replace that x in our integrand with just y to the 2/3, which matches our variable of integration, which means we're happy. So let's now do this as another step. So really our volume integral is from 0 to 8 of 2 pi. I'm going to put the 2 pi out front. Remember, that's just a constant. You can let those float out in front of the integral. And then x is going to be replaced with y to the 2/3. But then we also have that y that was there in the 2 pi xy. That y is still there. It's the x that got replaced. And then, of course, we still have our dy for variable of integration. Okay, let's take this a little bit further. We have the integral from 0 to 8. 2 pi is our constant out front. And then inside the integrand, we have y to the 2/3 times y. Well, just do a little basic algebra there. That means y to the 5/3. We just add those powers. And then we have dy. This is our integral. So let's go ahead and compute it. Of course, the 2 pi can stay out front. And then if we do the antiderivative for fundamental theorem of calculus here, I'm going to take that power and raise it by 1, which is really 3/3. That gives us then y to the 8/3. But then divide by that new power, which means I'm multiplying by its reciprocal, 3/8. So I have 3/8 times y to the 8/3 power, but I want that from 0 to 8. Now, this is just, again, some basic algebra, or really arithmetic at this point. You're plugging in 8 for y, and then subtracting, plugging in 0 for y. But the 0, of course, looks really nice because it disappears easily. So we end up with, or should end up with, double check it here, 2 pi times 3/8, that constant, times, I believe it should be 256. That is 8 to the 8/3 power. Which, if you plug or put that all together, I think it should be 192 pi. Again, double check the arithmetic on that. You can even check it using a calculator to make sure you get the approximate version of that, the 192 pi. But that should do it for our volume using the shell method for this problem. All right, let's move on to a third example. Number 3 says this: use the method of cylindrical shells to find the volume generated by rotating the region bound by the given curves about x equals 1. So we're not going around an axis this time, that is a plane axis. We're going around a vertical line, x equals 1. Okay, we'll get the picture going soon. And the curves bounding this region are y equals 4x minus x squared and y equals 3. All right, well, as mentioned, and as we've already been doing, let's go ahead and try to start with a picture so we know exactly what we're working with here. We'll have a horizontal x-axis, a vertical y-axis, and notice we're rotating this about the line x equals 1. I'm going to draw that line in, and I'm going to do it so that we remember that's the axis of rotation. I'll even make that in a red color. So we're rotating around that axis, not the y-axis itself. Okay, but then furthermore, let's get everything else on this picture. So y equals 3, that was the simplest. That's just this horizontal line going through, y equals 3 is a horizontal line hitting 3 on the y-axis. I'm just draw that in, hopefully well enough to see. Okay. Again, we're looking for accuracy, not artistry, but we want to make sure it looks believable enough. So there's our horizontal line boundary, y equals 3. Now we have this curve, this y equals 4x minus x squared. Well, let's think about that for a bit. If I make a simple xy table, then when x is 0, so is y. So we know there's a point at 0, 0. It'd be nice to know where it intersects the line y equals 3. So let's do a little bit of algebra for that. If I say 3 for y equals 3 equals 4x minus x squared for y equals 4x minus x squared, where do those intersect? We'll find out. Let's see, if I subtract 3 from both sides, we end up with 0 equals negative x squared plus 4x minus 3. And let's do a little more algebra on that. If you, let's see, it's easier to factor when it's positive, so just multiply everything by a negative. The 0 makes that pretty easy. That would just change all of the signs to be x squared minus 4x plus 3. And if we just try a little factoring there, then this would be, let's see, x minus 3 and x minus 1, which means when x is 1 or 3, we have these intersecting. So that means there's a point at 1, 3, which is right where the vertical line boundary we drew intersects the horizontal line boundary we drew. And then also when x is 3, so 1, 2, 3, that means 3, 3 is another point. Now, this is a rather kind of sharp looking parabola. It's just a downward facing parabola that uses these points as given. All right, so we know that, and that's enough. You know, where does it actually come back down and hit the x-axis? We don't really care, because all we're doing is rotating the region given, which is this kind of little bubble-looking region that's bounded by the parabola and y equals 3. And we're going to rotate that about the line x equals 1, which is this vertical line that we've drawn. And so it's not the actual y-axis. It's kind of pushed out a little bit from that. All right, so that's what's going on. In order to try to draw one of our shells, let's be careful here. I'm going to do this so hopefully we can see enough of it here. I'm going to draw it just so that the height of the shell is kind of just cutting right kind of through the middle of this little parabolic zone. And then I'm going to draw a 3D looking shell. Of course, the shell has some thickness to its edge because it's hollowed out. So let's remember that. And I'm going to, from that diagram, I think I'm going to redraw it so we can see a little bit better. We have just, as I've been doing, right, a 3D shell, which is really just a cylinder that's hollowed out. And what we care about is like the thickness, the radius, all that stuff, right? So let's try to make sure we understand where this is going. This shell has a radius that's extending from the line x equals 1 as given, which means the thickness of this shell would be a horizontal thickness. So this is a dx thickness. We care about that. That's going to orient our entire integral that we end up setting up. It's our variable of integration. We also care about the average radius. Let's kind of just take note of that's going from the center of the shell out to the average, the middle of the thickness. Then let's think about that shell or that shell radius for a second. Notice that would be extending out from the line about which we are rotating, which is actually this line x equals 1. So our radius is not going to be just x, right? Because if it were just x, that'd be like it extending from the y-axis. But this is extending from the line x equals 1. So we're going to have to make that x minus 1. You have to take away that space that's between where that x equals 1 line of rotation is and the y-axis. So you'd be taking that away to find the actual radius of this cylindrical shell. It's hard to draw in there, but it's important to kind of see. So it's the x distance, which would be anywhere extended out somewhere, within our zone. That distance, take away 1, means you're taking away everything between 0 and 1 to get the actual radius of the shells. So there's a lot to visualize there, but that's why x minus 1 actually makes sense. Going out to x, out to where you are in positive x territory, but then take away everything between 0 and 1 because that's not included as part of the radius. Okay, so our radius is going to be x minus 1, and everything else I think we should be able to kind of start putting together here. Let's see if I can make that a little clearer. We're taking that away. All right, let's get our volume integral set up. So we know volume equals the integral of 2 pi xy. We're just using our standard formulas defined above. Of course, we've already discussed in this one that our thickness for these cylindrical shells is a dx thickness. Now we're going to have to be extra careful in this case because if you can kind of imagine it, these cylindrical shells are floating away from the axes, right? Our axis of rotation is not the y-axis, and we're elevated up here above 3 as this lower kind of boundary horizontal line. So because of that, we have to be extra careful and rewrite this with a couple considerations. I'm going to rewrite this as the integral of 2 pi, and then instead of writing xy, let's think of it this way. Our x distance, our horizontal distance representing the average radii of all these shells, is going to be extending beyond 1. Now we've already represented this. Let's see, I'm going to re-highlight some things here. So we said x minus 1 is the radius length because you're extending out from where x is 1. But now notice the height, similarly, is not just a straight up y value. So let's see, the x distance is actually going to be x minus 1, as we'll see here. But the y distance, the vertical height, let's see, I'll make these purple color. The vertical heights are actually all above 3. Now they'll change depending on where you are for these shells, but here's the point. So we have 2 pi xy, but really instead of x, we're going to make it x minus 1, and again that just matches what we've already said for that radii representation of those shells. And then instead of y, we're going to do a couple things. So the function height of this parabolic curve is given as, I'm going to write this out here. So we want to match this as 4x minus x squared. That was just provided for us as the function definition, y equals 4x minus x squared. But then we're going to take away 3 because again, we're elevated everything above 3. So that's why that y expression is actually going to be the definition of the parabola, 4x minus x squared minus 3, because you're taking away all the space below 3 for those heights of those cylinders, because it's like floating out in space, both to the right and upward above that 3 mark. So there's a lot there to put together, but hopefully that's making enough sense. You can kind of go back and pause, rewatch, make sure you believe everything we have represented here. Now the bounds of integration will match the radii that are extending from 1, where x is 1, that's kind of our axis of rotation, and the furthest they go is where x is 3, as we've already indicated. So we're going to do that. We're going from 1 to 3 for our radii, which means that's our bounds of integration. So at this point, just a bunch of algebra. Let's see if we can take this a little bit further. So we'll say our integrand equals the integral from 1 to 3. You can put the 2 pi constant out in front of the integral if you'd like. And then we have x minus 1 times 4x squared, times 4x minus x squared minus 3, which is all bound in parentheses there. If we multiply all of that together, it's a lot of algebra. So try this out, check it. I think you should get negative x cubed plus 5x squared minus 7x plus 3. And again, that should be the result of multiplying the two polynomials we had in our previous expression. That is the x minus 1 times the 4x minus x squared minus 3. All right, and it's all of that, of course, dx, which means this is looking a lot better. The antiderivative shouldn't be too bad. This one, double check it if you want. I think it should turn out to be 2 pi times, see, the antiderivative should be negative 1/4 x to the 4th plus 5/3 x to the 3rd minus 7/2 x squared plus 3x. And this is all going from 1 to 3, our bounds of integration. You can double check the antiderivative there. So, doing a lot of simplification and the fundamental theorem, you're plugging in 3 for x, and then you're subtracting when plugging in 1 for x. So it's a lot of algebra there, but double check it. I think you should end up with 8/3 pi, which seems like a nice clean answer, but double check that in. You're plugging in 3, just using the fundamental theorem there, and then subtracting when you're plugging in 1 to this entire expression. Of course, you have the 2 pi out front. Use that to simplify. I think 8/3 pi should be what you get. All right, let's try a fourth example. This one says, use the method of cylindrical shells to find the volume generated by rotating the region about the region bound by the given curves about y equals 2. And the given curves are x equals 2y squared, y is greater than or equal to 0, and x equals 2. All right, well, as we've been doing, let's start with a picture because it's helpful to get an idea of what we're working with here. So we'll draw just kind of a basic horizontal x-axis, vertical y-axis, and then let's do a couple things. First of all, note that we're rotating about the line y equals 2. That is a horizontal line where y is 2. So I'm going to mark that in there. In fact, I'm just going to draw that in as a solid. That's our axis of rotation, you could say. Now, interestingly, that's not the x-axis, right? But it is horizontal. So that means we're going to have to do some adjustments like we did in the previous example. But we're going around that line or that axis of rotation. On that, we have some other constraints, so let's get these down. So x equals 2, that's the vertical line where x is 2. So we know we're going to be kind of cut off right there as well. And then we have this x equals y, 2y squared. Now you could think of that in a couple ways. That's like you can do just a basic table. Let's do that. So if we make an xy table here, when y is 0, it seems like it's in reverse in terms of which variables you're used to. We're used to y being solved equal to something with x. This is reversed. It's x equal to something with y. So let's plug in 0 for y, and in which case you get 0 for x. So that means 0, 0 is a nice point. You could think of this in terms of a sideways or a kind of inverted parabola if you'd like. So pick something else that's nice. Like, how about when x is 2, what is y? Well, if you plug in 2 for x, then I'm picking that because that's one of our boundaries, just to kind of see where things are. Right, so that would mean when x is 2, we'd have 2 equals 2y squared, just plugging it in. Divided by 2 on both sides, we have 1 equals y squared, which means y equals plus or minus 1. However, remember, when we say y is greater than or equal to 0, that means we're only using the positive version of that. So that's helpful to know. So that means 2, 1 is another point, which we'll mark. And we know our parabola curves upward toward that. So we can graph this curved region. Now, it's bound by x equals 2, the curve, and y being greater than or equal to 0. So that's really just this kind of solid region that's really touching the x-axis, but we're rotating that about this line y equals 2, which means we're going to get kind of an odd looking shape. Now, symmetrically speaking, if I were to try to sketch in the upper half, the imprint, if it were symmetrically bound, it would look, something like the same thing above. Of course, it's rotated, extending from this line y equals 2. So it's kind of hard to draw the full detail, but let's get at least a shell going on here. So remember, our shells extend out from the axis of rotation, which in this case is y equals 2. So a shell would look something like this. The height of it would be kind of laying on its side, right? The height of the shell would be kind of laying flat. And if we draw it symmetrically, which is not easy to do, let's see, then these shells would have a thickness to them that would be in this case, the thickness would be vertical. So it would be a dy thickness. And again, this all matters because of the way we're going to set up the integral. So we have to understand that this thing's kind of laying on its side. It's one of those sideways extending vertically shells, which is really just a bunch of those cylinders. Okay, so that means the radii of these shells, let's see, I'm going to draw one in. It would go from the line of rotation, which is this y equals 2 line. The radius would go all the way down to, it's an average radius, so somewhere in the middle of the thickness there. That would be our radius. Now that's a vertical value, so we'll keep that in mind when we start building our integral. And then the height, of course, of the cylinder is a horizontal value. That would be an x value. So let's see if we can start putting this together for a total volume. Remember, we can start with the basic definite integral, which is 2 pi xy times thickness. We said the thickness is a dy, so we'll put that in place. Now, as we put the detail of this together, let's keep in mind that the radii of all these, the average radii of any of these shells would be equal to the center, which is vertically at 2. That was our axis of rotation, the y equals 2. Take away the y value of the curve to get there. So let me highlight this. The radii distance is going to be 2, starting at the center. Take away the y value, the vertical distance that you would extend, formed by this curve, to get the y value of where that radius would hit the cylinder. So r equals 2 minus y, that's going to be our radius, and that's a vertical value, so we'll keep that in mind. But then also take note that the height of these cylinders, which we also need, the height of a cylinder is going to be an x distance, but it's going to be the further point 2 take away the curve distance that it takes to get there. So let's label this carefully. We have already marked on our graph. I'm going to make sure we have that marked as 1, because remember we have the point 2, 1 plotted. So I'm going to put the vertical mark of 1 on the y-axis there, clearly. 2 is where our axis of rotation is, and then of course 3 would be the top of our diagram, the symmetrically distant place above, where we have the other side of our cylinders kind of mapping on the top, right? So we have this set up. What matters is to put the integral together. We're going to have to use a definite integral with some bounds. I'm going to put the 2 pi just out front to give some, just to kind of move it out of the way there. So we have 2 pi times the integral. Now, where are these radii going from? Well, they're going from 0, which we're using the y values here, of this piece that's getting rotated around. So it goes from 0 all the way up to 1. Let me mark these in. Those are our bounds of integration. In fact, let me color coordinate these. So we're going from 0 to 1 as our bounds of integration. That's where this region is defined that we are rotating around. Furthermore, we have our x value. Remember, this is representing the height. So let me coordinate this as well. So the x is like the height of the cylinder, which is actually kind of on its side. So it looks like a flat length or something, but it's actually this height that we've marked in here of any of these cylinders. And then the y value in our integral, this is the going to represent or help us represent the radius. So kind of like we saw in the previous one, we have to make some adjustments here. So we have 2 pi just thrown out front. We're going from 0 to 1. And then we're going to say 2 minus y is our radius. Now let me highlight that in the same color. 2 minus y, again, because you're rotating from the line y equals 2, so take away the y value of our curve, and that's where the radius is at any of those places. So 2 minus y is our radius. And then our height, that is kind of laying flat, is going to be the furthest point down to the right, which is 2. Take away the x definition given, which is 2y squared. And let me highlight that in the appropriate color, representing our height. Oops, that's not it. That's the height of our cylinders that are laying flat. And of course, all of this is dy, which is making sense because all the variables of the integrand are y, and of course, our variable of integration is also y. So there's a lot to calculate here, but the setup is what's key. Look back through, pause it, check it again, see if that's making any sense. That's where we want to go to set up this integral. All right, let's finish this off. Of course, there's just some calculation remaining. You could even do a little bit of algebra kung fu here. If you factor a 2 out of this expression, we have 2 minus 2y squared. If you factor a 2 out of that, and then throw that 2 out in front with the constant already there, you could make that then a 4 pi out in front, then integral from 0 to 1 of what we had, which is 2 minus y in parentheses after that. And then if you've already factored out the 2, you'd have a 1 minus y squared in parentheses after that, dy. Okay, so it's just algebra here. Expand the integrand, use the fundamental theorem of calculus to find this antiderivative. You're going from 0 to 1. Double check it. I think you should get 13 pi over 3. Just go slow on the algebra there to see if you get that. Remember, you're doing the antiderivative, and then you're evaluating it from 0 to 1. Okay, and you have this 4 pi out front. Try that out. 13 pi over 3, I think, is what we should get. All right, let's do one more problem here. I know it's been a lengthy video here, but the last one here. This one says, number 5, the region bounded by the given curves is rotated about the specified axis. Okay, find the volume of the resulting solid using any method. So notice this time they're not telling us or forcing us to use any specific method like the shells or washers or discs or whatever. It just says use any method. Now the curves given are as follows: y squared minus x squared equals 1, y equals 2, and then it says about the x-axis. Well, as usual, let's start with a bit of a picture to help understand what this region actually is. So I'm going to draw just a basic horizontal and vertical set of axes, x-axis horizontally, y-axis vertically. We're going to have to remember a couple things. So the first curve given, the y squared minus x squared equals 1, you may have to go back and recall some algebra. That's actually a hyperbola. So that has, of course, it's just centered at the origin in this case. So you could reconstruct that a little bit, just sometimes using asymptotes and things. We'll do a bit of that as we go here. We know that the center of this hyperbola is at 0, 0. I'm just going to put a point there. The major axis, in other words, the one that has the branches, is the axis that comes first. just to remind you of some things with this algebra here about conic sections. This would go back to maybe intermediate or college algebra here, maybe a pre-calc. So you have y squared minus x squared equals 1. Well, that means underneath those variables, you'll find the square root of the distance you're going away from the center, which is just 1. So we're going to go up 1 and then down 1. Of course, in this case, we're having the major axis vertically speaking, so we actually have a point at 0, 1. And then you would go 1 unit in the x or horizontal direction as well. And you would draw a kind of phantom box of that dimension and then connect its corners to draw in those asymptotes, and then your hyperbola would be bounded by those slanted asymptotes, which I'm just going to draw in here as a bit of a rough sketch. All right, so it's getting an idea of what exactly we're working with. I'm going to take away all the other stuff that would be used to construct the hyperbola just because it's too much clutter in our picture. That's one of our boundaries. And then furthermore, y equals 2. Well, that would be, okay, so my picture is not that great. This is vertically 1, so we have a point at 0, 1. That's where this hyperbola actually would hit the y-axis. Redraw that a little bit. So we have a point at 0, 1, and then, of course, we have a line at y equals 2. That's our other boundary. I'm going to draw that in, make it a little bit faint, so you can see what's cutting off our region. So it's the space between the horizontal line y equals 2 and the bottom, the bottom of this zone is the top branch of this hyperbola that we've drawn. We've only drawn half of it. And that is getting rotated about the x-axis. Okay, well, at least we have a simple rotation axis here, just one of the standard, in this case, x-axis. And we're going to rotate that around. Now, notice then what would happen symmetrically. You'd have a point at 0, -1, and then a similar but symmetrical, set of branch kind of making up this hyperbola, of course. Y equals -2 would be the symmetrical boundary down there. And you'd end up with a 3D figure that is hollow on the inside because there is space between the curve and the x-axis. So in this case, it'd have kind of a hollowed out inside. Now, this may start to make you wonder, well, what should we use, right? In this case, you would not use a disc because of the hollowness to it. You'd have to use either a washer or maybe shells, right? And sometimes, honestly, both could work. So you'll just get familiar with what one you might like better, or looking at the actual provided information, which one might have simpler algebra. If you think simplicity on this one, I think washers are going to be nice, because think about this. If you put a washer, you'd be stacking them on the axis of rotation, which is the x-axis. A 3D washer which I will draw somewhat here, which has a thickness to it. And then, of course, it's hollow on the inside because it's a washer. So let me try to bring out a cross section of this. We're looking at a vertically oriented washer, meaning it would be like stacked on the axis of rotation, which is the x-axis, which means it would have a thickness to it that is in this case, horizontal thickness. So we'll call that thickness a dx thickness for a washer. Now, I think a washer makes a lot of sense to use here. Number one, it's hollow in the middle, so it has to be either a washer or maybe shells. But the algebra of washers is usually simpler, or could be, so let's try that out. Again, not that you would never be able to use both a washer and a shell, but in this case, I think we're going to find it useful just to stick with our simple washer formula. So let's recall what that would even be, right? We're looking for volume. And washers, of course, have a radius. So let's kind of draw this in. You have a large radius and then a smaller radius. So the larger one would go from the center of the washer all the way to the outside. That's capital R. And then you'd have a smaller radius goes from the center of the washer to the inner portion. That would be lowercase r. Now that larger radius is going to be stuck at 2, or fixed at 2, you could say, right? From the center of the washers all the way to the edge of them is as high as this goes, which is bounded by the line y equals 2 that was given. So that's going to be stuck at 2. That's not changing. The inner radius, however, is changing depending on where we are, right? So this would be now the vertical distance between 0 and, you could say, maybe the inside of, this hollowed out 3D solid. Now, what is that? Well, we're going to do a little bit of algebra work to get that, because the vertical height there is actually just the y value height of this hyperbola. So if we take the equation given for the hyperbola, which is, let's see, y squared minus x squared equals 1, and we solve this for y, this should give us that y value height. So let me add x squared to both sides. So y squared equals 1 plus x squared. We'll take the square root of both sides, which means y equals, y equals plus or minus the square root of 1 plus x squared. Now, it doesn't matter which we use, the plus or the minus, because it's going to get squared anyway. So we'll just use the positive version to keep it simple. So that, again, that height from 0 up to where this curve is, bounding the kind of the bottom of this solid that's getting rotated around, right? So we're going to call that then just the square root of 1 plus x squared, or you could say x squared plus 1. That's that smaller radius. So all we have to do now is put this in place for our value, our volume integral for a washer. And so going back to that, which again was a previous topic, that will have a pi, which we can let float to the front eventually as a constant, but for now we'll put it there. So pi times large radius squared. Well, for us, that was the value of 2 squared. And then minus the smaller radius squared. We already said that was the square root of 1 plus x squared and that's where the squaring's happening, which means it doesn't matter whether we use the plus or the minus. And it's all of this times the thickness, which we've already said is a dx thickness. So all we have to do is evaluate this integral. Let's go ahead and break this down again. Oh, and notice the x values. We need to figure out where they go from, right? So this is a symmetrical value. We're using washers, which means we could do half of it and double it, since it is symmetrically based. We want to figure out where the x value is at the end, where you could say where y equals 2 meets up with our hyperbola. So let's take a second to figure that out first so we can get our bounds of integration. And if you just go back and take the original equation of that hyperbola given, so that's it was y squared minus x squared equals 1. And we want to know, what if y is 2, which, by the way, is where the vertical horizontal line cutoff is, kind of bounding our region, right? So what if y is 2? Well, that means, let's see, 2 squared minus x squared equals 1. 4 minus x squared is 1. X equals plus or minus square root of 3, if we just do some algebra there, which means that's the horizontal place where these curves meet. It'd be the kind of left and right side, you could say, of where, as far as our solid goes. Okay, so what that means is if we're integrating with respect to x, x being our thickness here, then those values go from negative square root of 3 to positive square root of 3. But here's where the symmetry comes in. Since it is symmetrical about that span, you could just double it and go from 0, which really makes the calculation a lot simpler, especially if doing this by hand. So I'm just going to put a 2 out front as a constant and go from 0 to square root of 3. Again, this only works because it's symmetrical. And then you could even let that pi float out to the front if you'd like. And then you're really just integrating here 4 minus, if we square the square root, we have just 1 plus x squared. This is all dx. Okay, so the rest is history. You can combine some like terms. At this point, if you've stuck around this long in the video, you're ready to be done here. Okay, so we're just looking at the integral from 0 to the square root of 3 of, it's really just 3 minus x squared, if you simplify everything in the middle, dx, and that's just something you can compute using the antiderivative, fundamental theorem of calculus. I believe the answer should be 4 square root of 3 pi. You can double check that by just running through it, but that should give you the volume of that solid.